Hey guys, welcome back. Nachkazi here. In today's video, I'm gonna go deep into the Wi-Fi technology. If 802.11 does not ring a bell, I'm here to help. Today we're gonna do a deep dive. Are you ready to swim into the wireless Kool-Aid? Let's roll. Welcome to CCNA 200-301 course. Today, we're going to discuss Section 2, Part 3, LAN, Wired and Wireless. Today's session is all about wireless technology. We're going to do a deep dive. Here are the topics I plan on covering today. First, wireless LAN overview. Second, we'll look at different topologies. Third, we'll look at different standards and channels. Fourth, we'll look at different architectures. Fifth, we'll look at different deployment models. And finally, I'll wrap it up with wireless LAN security. Let's go. Wireless LAN overview. Wireless lives on layer 1 and 2 of the OSI model. In wireless LAN, we have radio frequencies that are radiated into the air from antennas that create radio waves. One of the things about the wireless LAN is that it behaves like a hub. And in a hub, if you guys recall, we have what's called a shared signal, meaning everybody that's connected into the hub, they're all sharing the same piece of wire, if you will. And the communication happens to be half duplex when it comes to the hub, meaning only one device can send data and it can only send or receive. It cannot both send and receive at the same time. It can only transmit in one direction. Either it's sending something or it's receiving something. That's half duplex. So the pictures at the bottom of the screen are showing us to the left of how a wired Ethernet hub looks like, and to the right we see how the wireless access point operates. It's the same idea. The only difference is you're changing the medium. Instead of a wired connectivity, we're now on the wireless radio frequency. Wireless technology uses CSMA-CA, which is Carrier Sense Multiple Access Collision Avoidance. And what that means is only one device transmits at any given point in time, and other devices use random back-off timers and have to wait their turn before they're able to transmit data. And each frame must be acknowledged by the access point before the next one is sent. And if the acknowledgement is not received, what ends up happening is we retransmit data. That's why on the wireless network, the actual throughput that we end up experiencing is a lot less than what's advertised by the access point manufacturer. And here are the two biggest challenges of the wireless technology. First, things like interference. So if your access point is behind a wall, for example, there's an obvious interference there. If there's a metal, there might be another type of interference there. Even things like moisture and dust in the air, believe it or not, could also potentially cause interference, and we'll discuss more details momentarily. And the second big Achilles heel of a wireless LAN network is security. If you think about it, guys, anybody who happens to be within the range of the wireless access point can communicate with each other. That includes everybody, good guys and the bad guys. And a lot of the bad guys actually exploit this because shared airspace is no different than you communicating in open public. Let's say you go to a coffee shop and you have a phone conversation and it's supposed to be a private conversation. Well, if you're speaking in a public space like a coffee shop, other people can listen to you. Similarly, on a wireless network that is publicly available to everybody. As you can imagine, everybody who's connected to that wireless network has the ability to eavesdrop and listen into anybody else's conversation. So that's a pretty scary thought. Security has come a long way since wireless was introduced back in 1999. Today, we're looking at really high levels of security, but one thing I want you to keep in mind is it has to be implemented properly for you to take advantage of it. Some additional basic terminology. SSID in the wireless network stands for Service Set Identifier. That's the name we connect to. So for example, if you fire up your wireless card on your laptop or your phone or your iPad for the first time, I'm sure you've noticed that you'll see a collection of different wireless devices that you can connect to. And then you'll find the one, for example, that happens to be your home access point. You'll pick that SSID, whatever you called it, that assures me that I'm connected to my own personal access point and not somebody else's access point. So this is how the wireless networks are differentiated. The service set piece here means group of wireless devices. One thing you need to keep in mind when it comes to SSID, both the receiver and the sender must have the same SSID for them to be able to communicate with each other. And there's another term that's used kind of behind the scenes is BSSID, or Basic Service Set Identifier. That essentially is a MAC address of the access point. Multiple access points can have the same SSID, but each access point has a unique BSSID. So what that means is, like I said, SSID is a logical identifier. So I can have an access point where I'm advertising different SSIDs. So on 2.4 gigahertz, and we'll talk about the different bands in a moment, but on 2.4 gigahertz, I might have one SSID. On 5 gigahertz, I may have a different SSID. However, both of those SSIDs will have a single BSSID because BSSID is a MAC address. And there are 3 different basic types of wireless sets, and there are 2 different modes. First one is called IBSS, or Independent Basic Service Set. Here's how it looks like. So in this scenario, we have direct communication between clients. There's nothing in the middle. There's no access point or wireless router or whatever have you. What you have here is a bunch of clients, laptops, PCs, whatever, or wireless devices talking directly to each other. That's considered Ad-hoc mode. Then there are 2 additional service sets. There's Basic Service Set. It's considered infrastructure mode. And in this mode, all wireless clients form a membership with the access point. So as you can see, all these laptops here are communicating with the access point and they form a membership. This membership is called association. So essentially, a client associates with the access point. Finally, there is ESS, or Extended Service Set. It's also considered infrastructure mode, similar to BSS. The only difference here is when you combine multiple basic service sets together via a wired LAN infrastructure, that's what makes up an ESS. And wireless clients associated with multiple APs using the same SSID. And ESS facilitates transparent roaming. So let's unpack this ESS a little bit. So like I said, multiple BSSs connected via a wired LAN infrastructure. So as you can see, there are 2 access points that are connected to a single switch here. Wireless clients are all using the same SSID as shown here. Both access points are advertising the same SSID. And this is what facilitates transparent roaming. So the roaming component, we'll talk more about it momentarily, is when this laptop, let's say A, moves into the territory of this access point to the right. When it does, we want this to be very seamless. We don't want the connections to drop because, as you can imagine, this is year 2021. Most of the people are on Zoom calls and WebEx and all that, and they might be communicating with somebody in real time. we do not want that call to be dropped or that WebEx session to be timed out. So we set up this transparent roaming where the user just walks around. Here you are only seeing 2 access points, but in a real world environment, in a large enterprise, you may have a ton of access points on a particular floor, for example. And as a user, as you walk around the floor, you don't even notice a blip. But in the background, you're experiencing transparent roaming that is facilitated by ESS, or Extended Service Set. Now let's look at a couple of design basics in real world when it comes to wireless LAN. So a cell is an area range covered by an access point. And one thing that I want to explain before I move further here is very quickly how a wireless client is able to connect to the access point. So the way it works is, first step is when the Wi-Fi client comes online, so let's say this guy A comes, you enable the wireless card, it issues a probe and sends it to the access point. The access point responds back with what's called a beacon, and the client associates with the chosen SSID. So at that point, let's say the SSID here is Naj. So when this laptop connects to this wireless SSID called Naj, initially it sent a probe. In response, it received a beacon back. Then it associated itself with the SSID. The last step in the process is that the access point adds this client's MAC address in association table. So this is how the access point is able to keep track of the different devices that are connected to it. Now back to the design. So as I said, cell is an area or range covered by an access point. And best location for an access point can be chosen by performing a site survey. So if you have no experience working with wireless networks before, what we do in real world in a corporate or enterprise type environment, if you want to deploy the access points in the correct fashion, what you would do is you would perform a site survey. It's an investigation process in which an access point is placed at its desired location and the client moves around. And as the client is moving, the signal strength is measured in real time. There are some special purpose devices too, but the cheapest method is to actually just place an access point where you would like it to be placed, and then you take your client, could be your laptop or iPad or whatever, and then you start moving around and see if you're getting the best possible coverage. As you can see at the bottom of your screen here, this guy Z is outside the range of this access point. So if the wireless signals are not getting to this Z guy, it's not going to be able to connect. So we would want to find the most optimal place for the access point. The clients outside the cell coverage, at the risk of stating the obvious, are unable to associate with the access point, right? Because they're not getting the signal. A couple of other elements I want you to keep in mind. In real world, clients roam from one cell to another. So in order to provide coverage, service areas should have 15% overlap. So let me quickly explain. So as you can see, these are all different access points, right? So this is an access point, this is an access point here, so on and so forth. And we got a client A at the bottom here. As this client is moving around or roaming, when we place multiple access points in our environment like this, we want to make sure that there's at least 10 to 15% overlap of these signals to allow for transparent roaming. Because if you can imagine, if there's no overlap, then there might be a point where as this client at the bottom is moving around, as they move from one cell to the next, there might be a dead spot or a dead zone. To avoid the dead zone, we need to have this overlap. If repeaters are being used to provide extended coverage, service areas should have 50% overlap. We'll talk about repeaters in a moment, but if you're using repeaters, then the overlap should be more because repeater repeats the signal. In order to provide extended coverage as shown below, the adjacent APs cannot use the same frequencies or channels. Once again, we'll talk about frequencies and channels momentarily, but you cannot have APs that are right next to each other or adjacent to each other and be in the same frequency range, because those frequencies are going to start canceling each other out. They're going to create noise and the signal is going to get lost. And you might have certain times when the signal just gets completely scrambled and collisions occur. That's the whole idea with the collision avoidance, right? We want to avoid collisions. And once again, the act of moving between APs is called roaming. Now let's focus on wireless LAN topologies. First topology I want to discuss is repeater. To extend wireless range or cell area, what we do is we add another access point. So here in this diagram here, typically an access point is connected to a LAN switch. And one thing I want you guys to keep in mind is the primary purpose in life for an access point is to provide connectivity between the wired Ethernet and a wireless Ethernet environment. So here, if you guys remember, 802.3 is the Ethernet, right? So that's a wired connection here. And this wireless right here between the access point and the laptop is 802.11. And we'll discuss more details momentarily. But what ends up happening is as this laptop wants to go out to the internet, for example, the wireless signal, which is encapsulated in 802.11, gets decapsulated by the access point. And then the access point encapsulates the same message into 802.3 message and sends it across the LAN out to the internet, for example. And then the same thing happens in reverse, the encapsulation and decapsulation, as the data comes back from the wired LAN infrastructure back into the wireless environment. That is something I want you guys to keep in mind. Now back to the repeater. What happens in the repeater scenario is we have an access point already, but then we have another client, let's say this laptop 1 at the bottom of the screen, which is outside the range of our primary access point. And let's just say for argument's sake that we do not have the ability to provide a wired connection into this laptop because it's not feasible. Either financially or physically, it's just not possible because it's out of reach and we don't have an infrastructure to support that. So what we would do in that scenario is we would add a repeater. And repeater is essentially a lightweight version of an access point. As a matter of fact, you'll find some access points on the market that allow you to change the functionality to a repeater. So you can, when you log into the GUI of that access point, you can just select the option that says, I don't want to use it as an access point. I want to use it as a repeater. And then when you do that, then it no longer acts as an access point. It takes signals from an access point and then repeats those signals for the clients to connect into. Now, it looks great on paper, but the reality is that when you repeat wireless signals, the quality degrades. And once again, the whole idea here is to increase the signal strength because the signal is dying, and at a certain spot, you might have a dead spot. So instead of having that dead spot through repeater, you can enlarge that area. But the drawback is that when you do that, it can significantly reduce the throughput of your wireless network because you're now repeating the same signals. And there's also a lot of interference that could potentially happen between the repeater and the access point as well, especially if they're on the same channel. So something to keep in mind. Not an ideal scenario, but something you can do. The next topology I want to talk about is Workgroup bridge. To bridge the wired and wireless network together, we have this Workgroup bridge scenario. And you can think of Workgroup bridge as an external wireless card for a legacy wired-only device. So here's what I mean by that. So you got this access point that's connected to the LAN infrastructure, but then you have this legacy client at the bottom. And this could be a legacy medical device, for example, right? And let's say that medical device only comes with an RJ45 connector at the back of it. It doesn't have any wireless capabilities, zero wireless capabilities. Well, how are you going to connect to the wireless environment. And let's say for some reason you can't bring a wired connectivity into that legacy client. And what if that legacy client has to move around? For example, if it happens to be on a cart that gets rolled from one room to another room in a hospital, for example, well, you cannot have an Ethernet cable dangling off of it, right? So what you would do then is you would have this device, which is a special purpose device called Workgroup Bridge. It has one leg in the wired world and it has another leg into the wireless world. And it bridges the two together and allows for this legacy Ethernet only, wired only device to be able to connect to the wireless network. And like I said, it's fairly common in a hospital type scenario, also in some legacy environments where you do not have clients with wireless capabilities. The next up is outdoor bridge, point-to-point and point-to-multipoint. So you could also have outdoor bridges. You could have, for example, two buildings that need to be able to connect to each other using special purpose antennas. And there are two different types of outdoor topologies. One is called point-to-point, the other one is point-to-multipoint. Let's talk about the point-to-point first. So as you can see here in this picture, I've got this building A to the left and building B to the right. And I've got this LAN switch that sits inside this building. And then I've got this bridge that has one connection into the switch and another connection that connects to a directional antenna. And this directional antenna is on both sides. And by pointing them toward each other, we can create this wireless connectivity between the two buildings. Now, in an ideal world, you would want to have some sort of like a fiber optic, physical wired connection between the two buildings. That's the most ideal scenario. But in some instances, it's not possible. And this is where this outdoor bridge point-to-point connectivity comes into the picture. Next, let's discuss point-to-multipoint. So here, it's very similar to point-to-point, but as you can see, there is another building in the middle here. So let's say this is building A, this is building B, and we got building C. Building B in the middle here has this what's called an omnidirectional antenna. And what that means is it's a type of antenna that is capable of transmitting its signal equally in all directions. So it can reach the other buildings simultaneously. So it kind of radiates its signal equally in all directions and allows those directional antennas to kind of amplify the signal, if you will. And this allows all three buildings to be connected with each other. Next up, we got the mesh network. This is a specialized type scenario. So in a very large environment, we can create a mesh topology to allow wireless traffic to be bridged from one access point to another until it reaches the wired LAN infrastructure. So let me show you here. So as you can see here, we got all these different access points and only one is connected to the LAN infrastructure, but the rest are all connected to each other as repeaters. And it's what we call daisy chaining of APs, and it offers transparent roaming. And typical use case is a university campus or a sports stadium with thousands of potential people that want wireless connectivity. Now, when you think of a mesh network, you might think, oh, repeaters are bad ideas, so mesh networks must be horrible. That is not true. Cisco uses its own proprietary mesh network protocol for wireless connectivity, which is pretty intelligent, and it figures out how to collect all the traffic and then bridge it across all the way to the wired infrastructure in a seamless fashion. Plus, it has some interesting auto-healing capabilities. So let me explain. Let's say if this guy dies. Well, if you're using a mesh network configuration, what's going to end up happening is this access point right here and this access point right here, they're going to automatically increase the power transmission of their radio frequency, so the signal strength increases, and they're going to end up making up for the slack of this access point that just died on us. So it's really interesting, it's really cool, and in a large environment, that's what you would typically see set up, where you don't have the ability to connect each access point physically back into the LAN. In an ideal world, you would want every single AP to be able to connect back into the LAN infrastructure with the physical Ethernet cable, but that's not possible in some scenarios, and that's where the mesh network comes in. Now let's discuss different wireless LAN standards and channels. First, let's discuss radio frequency. RF, or radio frequency. That's what the wireless local area network is all about. So when I think of radio frequency, what I think of is radio in your car, and you have this FM stereo player in your car. What you do is you have either AM or FM channels, and you can connect to 92.3, and you might connect to hip hop. And if you switch it to 96.6, you might connect to jazz. And if you switch it to 99.7, you might connect to classical music. So what you have as you switch from one frequency in FM to another frequency, you're basically hopping channels. You're tuning into different channels. And that's exactly what we do in the wireless LAN network. And what we have in the wireless LAN network, two different unlicensed frequencies that are dedicated for wireless communication. The first one is 2.4 gigahertz band, and it's a range that starts at 2.400, goes all the way up to 2.485 gigahertz. And the other one is 5 gigahertz band, and the range starts at 5.150 all the way up to 5.825 gigahertz. Once again, these are different. You can think of these as different radio channels. Lower frequency translates to longer range, but the data rates are lower. So for example, 2.4 gigahertz frequency has a higher, longer range, but the data rate drops because it extends the signal. So the longer you extend the signal, the less it has the ability to deal with high throughput data. And the inverse is true, or the reverse is true. Higher frequency equals smaller range, but the data rates are higher. So the 5 gigahertz band, for example, that's higher frequency. The range is smaller with 5 gigahertz, but the data throughput is higher. And radio frequency signals are negatively impacted by a couple of different things. And there's a whole slew of different things we can talk about, but the ones that I wanted to highlight are things like reflection. So if you have like a mirror or metal, wireless signal kind of bounces off of it, right? So that's reflection. And refraction is where the signals bend after they hit either the water surface or certain type of surfaces. The signals bend. Absorption is like signals going through the wall. If the wall is made up of certain type of material, your signals may not make it to the other side of the wall. So that's absorption. And finally, scattering, where the signal just kind of scatters everywhere. So these are problems, these are issues that the wireless LAN suffers from, and we have to be cognizant of that as we're designing our wireless network, because these things can have an impact on the overall quality of our wireless LAN. Now let's dig a little bit deeper into the two different bands that we talked about, 802.11 bands in particular, 2.4 gigahertz and 5 gigahertz. First, let's focus on 2.4 gigahertz. So 2.4 gigahertz has 14 channels. These are called wide channels. Each channel covers a frequency range that is allocated to more than 4 consecutive channels. So let me explain. So if you look at this channel 1, for example, it has this frequency that kind of bleeds into some of the other channels. So for example, 2, 3, 4 are all impacted by channel 1. And then as you can see, channel 6 starts, and channel 6 then also kind of bleeds into different channels. It's bleeding into 5, it's bleeding into 7, 8, 9. And then we have channel 11 here. And channel 11 also bleeds into 12, 13, 14, and also partially number 10. So what does that mean for you as a consumer? It means at a 2.4 gigahertz level, you only have 3 non-overlapping channels, meaning you have 3 clean channels that you can use in your environment. Why is this important? Well, if you have an environment where you expect a lot of devices to be connected, also known as high density environment, then you may not find that 2.4 gigahertz is sufficient enough for you because it doesn't offer you enough non-overlapping channels. And like I said, you do not want channels to overlap. If they overlap or bleed into each other, then they cause interference, and interference results into collisions, and collisions are bad, right? Which means drop packets, and we can have a lot of retransmission going on our wireless network, and we don't want that. So that is something I want you to keep in mind, that this is a limitation with the 2.4 gigahertz band. And the only channels that are your friend are 1, 6, and 11. You should avoid using any other channel altogether on a 2.4 gigahertz band. Next up is the 5 gigahertz band. Channels here are narrow, as you can see in the picture here. Using 20 megahertz, we can have up to 24 non-overlapping channels. 5 gigahertz offers better throughput than 2.4 gigahertz because you have more channels available to you. And there's also a technology called channel bonding that allows us to bond multiple channels together. Let's say at 5 gigahertz, if each channel is 20 megahertz, if we bond 2 channels together, that would be 40 megahertz. And if we bond 4 channels together, that would give us 80 megahertz. And when we do that, what that does for us essentially is it increases the throughput quite a bit. And that's what we're experiencing with the technologies that we have in place today. Now let's look at different 802.11 standards that are out there. In the beginning, 1997 is when the wireless technology was introduced. Can you imagine a life before wireless? I cannot. So it's kind of humbling looking at this table here. It was at 2.4 gigahertz, 5 gigahertz wasn't supported, and the maximum data rate at the time was 2 meg. Then in 1999, 2 years later, we had 802.11b. And once again, it supported 2.4 gigahertz, did not support 5 gigahertz, and it was quite a significant jump, 11 megabits per second in throughput. Then 802.11a came out the same year, but it was on the 5 gigahertz band, and it offered a much better throughput, 54 megabits per second. But the reason 802.11a never took off is because at the time when B and A were introduced, there was a special silicon chip inside the access points that needed the 802.11a technology to be implemented. That was actually in shortage on a global scale. And because it was in shortage, 802.11b standard took off, even though technologically it was a lot less superior than 802.11a. Then 802.11g came out in 2003. It also supported 2.4 gigahertz, but then the maximum data rate went up to 54 megabits per second. Then in 2009, N standard came out. It supported both 2.4 gigahertz and 5 gigahertz with a total maximum throughput of 600 meg. Then in 2013, standard AC came out. Did not support 2.4 gigahertz, only supported 5 gigahertz and a maximum throughput of 6.93 gigabits. And finally, the IEEE standard 802.11ax came out in 2019. This is the latest standard available today, supports both bands, 2.4 gig and 5 gig, and is 4 times the data rate of 802.11ac, which is absolutely insane. But to take advantage of this kind of throughput, you need all the wireless clients on your network that support 802.11ax. And that is the biggest challenge. In real world, your wireless clients are always going to be a few years behind. So if you think of your laptop or your desktop or your phone or your watch or any device that needs Wi-Fi connectivity, you're going to find that most of those devices you bought a few years ago, they probably support an older standard. Even if you buy the latest and the greatest access point, that doesn't magically mean that everything is going to start communicating at 802.11ax. Both the client and the access point must have the appropriate hardware and software capability to support 802.11ax. Now, to further crystallize these 802.11 standards, because I know when I was a student for the very first time and I heard about these standards, it confused the heck out of me. So I want to help you understand these in a much simpler manner. So think of it as your cell phone. A couple of years ago, we were all on 3G, and then 4G came along, and most of us are on 4G today. And some of us are lucky enough to live in metropolitan areas that actually have 5G connectivity, and we're enjoying the higher throughput of 5G. But the idea is that as we move from the previous generation to the next, 3G to 4G to 5G, it's inherently understandable and understood that 5G is better than 4G and 4G is better than 3G. So with this in mind, I want you to re-look at the table we just looked at a moment ago. So here's that table again, but pay attention. To the left, there's more information. So a nonprofit organization called Wi-Fi Alliance introduced this idea of Wi-Fi Gen or generation. And the reason they did that is to make it simpler for people to understand, because as you can see, these IEEE standards have no rhyme or reason. Like we start at B, then we went to A, then we went to G. What happened to everything in between? Then we went to N, then AC, and now AX. There's kind of no rhyme or reason behind these different 802.11 IEEE standards. So the Alliance, the Wi-Fi Alliance, took it upon themselves to make it easier from a marketing perspective for people to understand how these different Wi-Fi standards operate. So very similar to 3G, 4G, 5G we just talked about a moment ago. If you have an access point that supports Wi-Fi 4, then you know it's 802.11n and these are the capabilities. And if you have Wi-Fi 5, then you know the capabilities, and so on and so forth. But where it makes the most sense is when you are talking to your upper management. Let's say your boss wants you to upgrade the wireless infrastructure. When you're talking to your upper management, instead of talking about all this technical mumbo jumbo, you can just say, I'm currently investigating Wi-Fi 6 solution. Because I believe in order to protect our investment, we need to be on the latest and the greatest technology so we can be protected for the next 5 to 7 years, if that happens to be your refresh cycle. And a couple of other things Wi-Fi Alliance did that I think are really cool and worth mentioning. If you see this symbol with the digit 4, that signifies Wi-Fi 4. If you see the symbol with 5, that's Wi-Fi 5. You see the symbol with 6, that's Wi-Fi 6. If you see these icons on a box When you purchase an access point, then you automatically know that access point you just bought has that capability, or it belongs to that particular Wi-Fi generation, if you will. And anything that's Wi-Fi certified, you'll also see this logo on there. And if it's Wi-Fi 6 certified, you'll see the Wi-Fi 6 certified logo as shown on the screen. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.